Hey guys, in today's video we're going to be looking at predicting the products of reactions between ionic compounds. Specifically, we're going to be using the solubility rules we learned in the last video to be able to take products and determine not only what they will be, but also determine their state, whether they're going to be aqueous or solid. In today's video, we're going to focus in on a handful of different reaction types. We're going to be looking at single replacement, double replacement, decomposition, and specifically looking at acid-base reactions. And remembering back to single replacement reactions, this is where an element is going to simply replace either the cation or the anion in a chemical compound. Let's take a closer look at a single replacement reaction. Now, in a single replacement reaction, let's say A, my element, is a cation. This means it's likely a metal. Now, if A is a cation and B is a cation, then in a single replacement reaction here, A is simply going to replace B, and my products will be B as an element by itself, and AC, which is our new compound. Now, if A was an anion, instead of replacing B, A would simply replace C. A as an anion would, generally speaking, be a nonmetal and or a polyatomic ion. Let's take a look at a double replacement reaction real quick. So if I have AB reacting with CD, then as a result, what I'm going to end up with is the A and the C switching places, and I end up with AdCB, where C and A are both my cations, B and D are both my anions. As you can see, they've switched places. Now, in our solubility reactions, this is going to be the most common type. It's going to be very common because we have to really look at solubility rules here. For example, in the reaction between sodium chloride and silver nitrate, I end up predicting the products are going to be sodium nitrate and silver chloride. And silver chloride, as we learned in the last video, is insoluble. So that's a solid. And we need to be able to predict that and know that for future chemical equations and also for understanding solution stoichiometry, which we're going to get to later in this unit. In decomposition reactions, we take a single thing and we break it apart into component parts. For instance, mercury 2 oxide, which I have here, is going to break apart into mercury by itself and oxygen gas. So you can see it's a decomposition reaction. And again, our solubility rules come into play if we're breaking down into component parts that are either soluble or insoluble in water. Now, in decomposition reactions, you're not always going to be breaking the actual compounds apart the way you would in, say, an ionic situation. For instance, in calcium carbonate, CaCO3, it doesn't break apart into calcium ion and carbonate ion. Instead, decomposition is going to result in calcium oxide, CaO, and carbon dioxide, CO2. Similarly, in potassium chlorate, what's going to happen is it's going to break into calcium chloride, KCl, and oxygen gas, O2. And when we take acids and bases and decompose them, they don't break apart into their ionic components. Instead, what they're going to do is break into binary oxides and water molecules. For instance, nitric acid, HNO3, breaks apart into nitrogen, dinitrogen pentoxide, and water. And for a base, potassium hydroxide is going to decompose into potassium oxide and water. We've already discussed the importance of particle diagrams in chemistry. This is another instance where we're going to be able to use particle diagrams to represent what we're talking about. For instance, if I have a predicted reaction, not only am I going to have to be able to write that in the form of a chemical equation, but I'm also potentially going to have to draw that in a particle diagram where all of my molecules or ions or any component part of the reaction shows up in both reactants and in products in the right ratios. So if we look back at an example from earlier, the decomposition of mercury 2 oxide, what we see is that mercury 2 oxide is going to decompose into mercury and oxygen gas. To balance this reaction, what we had to do was say, okay, well, 2 formula units of mercuric oxide or mercury 2 oxide are going to break apart into 2 atoms of mercury and 1 molecule of oxygen gas, O2. So to turn that into a particle diagram, what I'm going to have to do is make sure that my particle diagram represents both the formula unit of mercury 2 oxide together in the reactants and each component part in the products. Make sure you pay very close attention to the keys. Oftentimes the legend or the key is going to represent the atoms or molecules as needed, but sometimes they won't, and you're going to have to create one yourself. Make sure when you're doing this you represent not just the atom's identity, but also the relative size. In many cases, the relative size is just as important. Acid-base reactions are unique double replacement reactions. Now, in this situation, we call it neutralization because what's going to happen is the products of an acid-base reaction are almost entirely going to compose of water and a salt. Now, be careful. It's important to understand that neutralization does not mean that the end product is always going to be pH 7 neutral. We'll talk about this more when we get to the acid-base unit. In an acid-base reaction, what's going to end up happening is we're going to have the H+ ion from the acid reacting with the OH- cation from the base. In this situation, we create water, and as a result, what we end up with is that the anion from the acid and the cation from the base will combine effectively into a salt. Remember, before you complete any problem where you're predicting the products of reactions, you have to determine one of a couple of things. Number one is with what ratios will they be in, so that means balancing the overall reaction properly. And number two is what state will your products be in? Will they be aqueous? Will they be gaseous? Will they be solid? Or will they be liquid? Let's take a look at an example problem to show you what I mean when I talk about predicting the products of reactions properly. We're going to take, in this case, lead 2 nitrate and react it with sodium iodide. First thing we need to do is predict our products. If we look at this, there are 2 compounds involved, which tells us that it must be a double replacement reaction. That means we need to swap our cations. What we're going to do is we're going to simply rewrite with lead iodide and sodium nitrate. Now be careful here. Remember, it was lead 2 nitrate. In the products, it's still going to be lead 2, which means now it's going to be lead 2 iodide. Lead 2 iodide means that we need it to be PbI2. Remembering the crisscross method from our Unit 1 discussion of naming and writing ionic formulas, Unit 1 told us that we need to take the charges, lead 2 plus in this case, and iodide 1 minus in this case, crisscross those charges, so we end up with PbI2. So lead 2 iodide and sodium nitrate. Now sodium and nitrate both have +1 and -1 charges respectively, therefore they're in a 1-to-1 ratio in the products. So we've written the products, now we need a balance. When we balance, we realize that we have 2 iodides on the product side, which means we need 2 on the reactant side. So we need to put a 2 in front of the sodium iodide. That means we need 2 sodiums on the product side as well. That means we need to put a 2 in front of the sodium nitrate on the product side. The final step is to determine solubilities. We look at our products. Lead iodide, lead 2 iodide, is insoluble. Therefore, it will be a precipitate or a solid, whereas sodium nitrate is fully soluble, therefore it will be aqueous. If I were to ask you to put this reaction in the form of a particle diagram, what you'd have to do is look at the relative solubilities of each component, and if it is soluble, like aqueous, such as the lead 2 nitrate or the sodium iodide, in the reactants here, in the box showing reactants, we have to show them separately. Remember to create your own legend if one doesn't already exist. We're going to show the sodium and the iodide and the lead and the nitrate all separately. In many cases, size is going to be critical for representation. The sodium ion is going to be substantially smaller than the lead ion, and the iodide ion is going to be substantially smaller than the nitrate ion simply due to relative size of the atoms involved. We do the same thing when we're looking at our products. In this case, however, the lead 2 iodide is insoluble, so it actually is going to stick together, so we show it as such. Now, the reality is when it sticks together, it's going to be much more complex than this. It's going to crystallize, it's going to form a crystal lattice, so we're not going to just see one formula unit by itself. Instead, what we're going to see is a series of these, but for representation of particle diagram, we don't have to show that. We can simply show 1 or maybe even 2, depending on the number that you had on the reactant side, to show properly the ratio. And for sodium and nitrate, because of the fact that they are still aqueous in the product side, we're going to go ahead and show them still separate and in the same numbers as they were on the reactant side to show conservation of matter. Now I'm going to have you guys finish some reactions. So you're going to have to predict the products and the relative states of each product from these following reactions. Let's go ahead and do it. How about you predict the reaction of aluminum oxide? Just by looking at this, hopefully you recognize the fact that aluminum oxide is just one reactant. This means it must be a decomposition reaction. And in decomposition reactions, we break down into component parts. In terms of oxides, we're going to break down into aluminum atoms and oxygen molecules. Let's do balance. In order to balance, there needed to be 2 aluminum oxide formula units on the reactant side, 4 aluminum atoms, and 3 oxygen molecules on the product side. Now go ahead and turn that into a particle diagram. I'll give you a second to go ahead and draw this out. All right, go ahead and compare your particle diagram to mine. Make sure that the ratio of reactants to products is the same. Make sure that the number of atoms of aluminum and oxygen in both your reactants and products are the same. We need to make sure it's balanced in terms of the overall reaction, but also that we show conservation of matter in our particle diagram. Take a look at this reaction. Let's predict the products. Hopefully you recognize that this is an acid-base neutralization reaction. In this case, hydrofluoric acid is going to react with sodium hydroxide. It's going to create H2O, and in this case, NaF. In this case, because all of the charges are 1 to 1 to 1 to 1, it's already balanced. And in terms of predicting the solubilities of products, sodium fluoride is fully soluble because sodium is an alkali metal, and any compound that it is in, therefore, is fully soluble. If we were to show this as a particle diagram, go ahead and give that a shot and see what you get. Now, the key to this particle diagram is recognizing that the water as a product is together. It is liquid. So when we create our products, we need to show water, H2O, as simply a molecule. Now, in this last one, we're going to take silver nitrate, and we're going to see what happens when it reacts with potassium chromate. As a result, let's see what we get, and make sure, remember, you predict both the ratio in terms of balancing, but also the states of the products. In this double replacement reaction, we're simply going to swap our cations, so we end up with potassium nitrate and silver chromate. We need to make sure we balance. Silver chromate is Ag2CrO4, so we need 2 silver nitrates on the reactant side. We also need 2 potassium nitrates on the product side, so therefore we're balanced. So that wraps up today's video. Let's do a quick recap. Today we learned how to predict the products of reactions and use our solubility rules to do so. We showed how to use particle diagrams to represent this and make sure that we represent in particle diagrams not just the state of our products, but also the relative ratios of reactants to products in the balanced reaction. I'd like to thank Nicole Gaikova and Leah Ghazali for writing, filming, and editing this video. I'd like to thank you guys for watching it. I'll see you in the next one.